Good afternoon, good morning, good evening, everyone. I am Amal Kasri. I'm a Chief of Basic Sciences and Engineering at UNESCO. It's my pleasure to welcome you all today. Distinguished guests, dear speakers, ladies and gentlemen, it's my great pleasure to welcome you all to the fourth webinar in the Physics for Society series, jointly organized by UNESCO and the International Union of Pure and Applied Physics. This colloquia series is held under the framework of the International Year of Quantum Science and Technology, which actually is coming to an end quite soon. Through the IYQ, we are celebrating the remarkable achievements of quantum science while also reflecting on how to make the new wave of technological progress more inclusive, equitable, and sustainable. The Physics for Society Colloquia were created with a simple but powerful goal: to connect science with society and to bring together scientists, policymakers, and industry leaders to explore how physics, and especially quantum science, can serve people everywhere. Today's session will focus on the critical role of industry in advancing quantum innovation and social development. Quantum technologies are transforming our world from energy and communication to health, computing, and materials. So these transformations are not driven by science alone. They depend on the creativity, the courage, and the long-term vision of industry, which remains the true engine for innovation. I am particularly delighted that today we are joined by five distinguished industry leaders who will participate in our round-the-table discussion. Their experience and perspectives will help us better understand how the private sector can contribute to building an open, responsible, and inclusive quantum future. At the same time, I want to emphasize that with such power comes responsibility. Industry has a unique role to play in ensuring that quantum progress benefits all humanity. By helping to bridge the growing gap between the global north and the global south, which is a great concern for us here at UNESCO. This is not only a matter of fairness, it is actually essential for the sustainability and legitimacy of the quantum revolution itself. At UNESCO, through our Global Quantum Initiative, we are building a cooperative platform that links science, policy, education, and industry. And our aim is to strengthen open science, capacity building, and the ethical frameworks so that the global quantum ecosystem grows in a responsible, inclusive, and human-centered way. I would like to sincerely thank all our partners from academia, from industry, and from the international organizations for joining us today. Your insights and the collaborative collaboration make these dialogues truly meaningful. Let us ensure that the quantum revolution not only advances technology, but also drives fairness, responsibility, and shared prosperity for all. So I wish you all, I'm really looking forward to hear to listen to all of you and your insights, and I wish you a fruitful discussion. Thank you very much.
So
Christine, over to you. Thank you.
Thank you very much, Amal. So it was a very nice introduction. So for this fourth webinar that has been organized in partnership between the IUPAP and the UNESCO. So my name is Christine Darf. So I represent here the IUPAP. So where I share the Working Group 14 on accelerator science while working at the European Spallation Source, in Sweden. So we are delighted to welcome everyone to this forum, and especially our esteemed guests. So a true intersection of industry and quantum worlds. So this is the path for the future. So the International Union of Pure and Applied Physics, so this IUPAP, so this is the only global union covering all the different fields of physics. So it promotes international research collaboration, education, and the application of physics for societal benefits through its commission, working group, and partnership. So we are really pleased to have here as well with us, Sylvina Pons-Dorsson, our new IUPAP president. So we will conclude the event and share more insight of the IUPAP rejuvenation and the strengthening as well of connection with industry and the emerging physics disciplines as well. So the IUPAP was founded in 2022, so last millennium, I would even say, so 2022, with Sir Williams Henry Bragg, who was the serving first president. And he, to recall you as well, so he shared in 1915 the Nobel Prize in Physics with his son, Lawrence Bragg, for their groundbreaking works on analyzing crystal structure using X-ray. So this is the achievement which is fundamental for X-ray and neutron scattering community. So that's why I make this bracket. But today, so this IUPAP is unifying all the different physicists around and across the globe. So it's connecting the major facilities, the research organization, and the different universities. So it fosters collaboration that bridge classical and quantum science, driving innovation in fields ranging from material research to cutting-edge quantum technology. So this is why we have today this nice panelist. So the way we will structure this an hour and a half will be by short presentation, so with some slide by Matthias Streuer, sorry, and so Professor Obasi Shira. So I will mention the introduction of their work. Then we'll have a panel discussion, which will be with all of the guests that we see on the screen now. And we will finish by having an opening question to the audience. So you have a Q&A box, and you can already, during the presentation, write your questions. So we'll try to address them at the end of this presentation. And then we'll have the closing remarks. So we'll see Sylvie now. So first, and I will come back to introduction of Dr. Matthias Streuer, and we'll have first my colleague Jen Zio, who will introduce as the International Year of Quantum Coordinator through the UNESCO, her presentation.
Thank you, Christine, and good afternoon, good morning, everyone, and a very warm welcome to all of you joining us for this new session of the International Colloquia on Physics for Society. The series was launched by UNESCO and IUPAP under the framework of the International Year of Quantum Science and Technology 2025. With the vision of connecting physics and society, showing how fundamental sciences can inspire innovation, foster collaboration, and contribute to sustainable development. And over the past few months, we had 3 inspiring sessions that explored physics in action across different regions and contexts. And for this year, we're focusing on quantum. Our first colloquium was held on the World Quantum Day, featured Nobel laureate Professor Anne Lullier, who reminded us of the power of education and the role of physics in addressing global challenges. She also shared her experiences as a female scientist in the field. The second session on synchrotron science and science diplomacy showcased how large-scale research infrastructures from Sesame in the Middle East to the African Light Source Initiative can strengthen cooperation, build scientific capacity, and open new opportunities for the Global South. The third event, led by Professor Andrew Forbes from South Africa, introduced us to the world of quantum structure light and highlighted the growing momentum of Africa's quantum technology initiative. And today we turn to another vital dimension of quantum ecosystem, the industries. The session will explore how global companies and innovative startups are bringing quantum science and technology from the lab to marketplace, integrating it into real-world applications, and creating pathways for inclusive growth. We're truly delighted to have this distinguished speakers and representatives joining us from Quantinuum, IBM, Microsoft, QSAN Technologies, and Dr. Estelle Inak from Cameroon. And together, we will discuss how collaboration between industry, academia, and policy can shape a quantum future that is not only technological advanced, but also ethical, inclusive, and sustainable. And thank you for being with us.
Thank you very much, Sodine. It's perfect to have this overall introduction so that we can now have the panel, so that, no, not the panel, sorry, the keynote presentation. So first, I will introduce Professor Matthias Troyer and Professor Urbasi Sindha. So in introduction of, Matthias Troyer as a technical fellow and corporate vice president at Microsoft Quantum, so leading the quantum computing strategy and application. So born in Austria, so you became professor of computational physics at ETH in Zurich. So you're a pioneer in developing those high performance and quantum simulation. So you founded the open source ALPS, project that makes all those advancing algorithms widely accessible. So today, your work is bridging as well the quantum science and practical technology and advancing the scalable quantum solution for the global impact. So he will be our first speaker, and I will then introduce later the second speaker. So maybe we could have the presentation from Professor Troyer. Perfect.
Matthias, you have to unmute.
So we see the screen and you need to unmute.
Yes, can you hear me now?
Yeah.
Yes, so thank you for the invitation to speak here. It's an honor, and I tried to bridge the near North and the near Global South through my affiliations with Microsoft and with Stellenbosch University. And I'd like to talk on kind of what I learned kind of from quantum once I joined the company. And basically, the key thing is scientific discoveries always lead to new technologies. Thermodynamics led to the steam engine and the industrial age. Electromagnetism led to telecom, computers, and the Silicon Age. And now, since 100 years, we have quantum, and we are at the start of the quantum age. So the question becomes now, what will that change for computing? What will that change for science? What will it change for business? And there, the question I asked first is, I want to build a utility-scale quantum computer, which for me as a scientist was a machine with which I can solve those scientific challenges that I tried to solve with classical computers but could not. So it's about solving an interesting science problem that I could not do classically. But moving to a company, things have sharpened a bit. And DARPA was the first to push us that utility scale shouldn't just be that I can build a machine the size of CERN or something where I do one beautiful paper with many authors. Okay, that's great for science. But for business, we need more. There we need a machine that solves a problem where the value of solving the problem exceeds the cost of the computation. And with that, we need something that can scale. With that, we need something really that I can't do classically and that has an impact on the world. With that, we can now think about where are these problems, where we can see that the value of the calculation can exceed the cost. When we look at the quantum machines, they are much more complex than a classical computer, meaning every quantum operation will cost about 1 billion times more than a classical transistor switch. But if we have exponential quantum speed up, then the quantum computer will win. So they will be good for small data problems and not big data problems. Small data problems simply because loading data is also more costly. Thus, looking now at the small data problems with more than a polynomial quantum speed up, one thing that is well known is Shor's algorithm for breaking crypto. But there's no value in that. There's no business value in that. There's no value for society in that. But one more problem that we know will be able to solve will be solving quantum problems, simulating molecules, simulating materials. So as your Feynman said years ago, if we really want to solve a quantum problem, if we want to simulate nature, then I better use the quantum computer. So that's what we focus on, because that's what we see as the first application. And that will do not just with quantum, but we'll do it combining AI, supercomputing, and quantum in the right way. So let me share with you why I think that will be the future. We looked at it already with the AI, and as you know also from last year's so the Nobel Prizes in physics and chemistry, the AI is really changing science now. And we, for example, showed the power of AI by screening 32.6 million new potential materials in less than a week to find a new electrolyte for a battery, so the solid-state lithium battery that uses less lithium than existing ones. So there's lots one can do doing science faster with AI. But these models we use there, they are trained on classical data. And if I want to simulate molecules or materials with classical computers, then the cost increases when I want the accuracy to increase. When I just want the structure, the geometry, I can do that with classical force fields, molecular dynamics, protein folding problems are well solved with classical methods with linear scaling. When I want to go to electronic properties, I'm using the density functional theory. The cost becomes more expensive now, cubic in the size of the problem, still doable in minutes or hours on a supercomputer. But when I want to look at chemical reactions, chemical processes, light matter interactions, then I need more than that. Then I need to look at the correlated states, and then the scaling can become exponential in the size of the problem. And that's where quantum comes in. With quantum, those problems become easier. With quantum, I can solve the hard problems, the correlated systems in a time that scales polynomially. So the quantum computers will let us solve problems accurately that we can't do classically. They will thus make things more accurate. If I want to calculate faster, I'm using AI. I train the models and then I do the inference to predict what I would get. And guess where the future will be. The future will be combining the two. The future will be combining quantum and AI to get models that are quantum accurate, but as fast as the classical models we have now. So the path for that is, I'm starting by simulating molecules that I'm interested in. And today I do that with classical supercomputers. I use the results to train a model, and from that model I can much faster, 10,000 times faster sometimes, predict the properties of materials, but only as good as the classical simulation is. And that is often, unfortunately, not good enough. When we get a scaled quantum computer, then we get better data, and we can refine the models with that better data, and thus then get models that are quantum accurate and fast. And then we'll be able to actually predict properties and chemical reaction, chemical processes much better. That can then go from problems of clean water, clean air, capturing carbon from the air, better fertilizer, better drugs, and so on. There are many things we can do with it. by combining quantum and AI. Because then we'll be able to just predict the material with the proper tier 1. They can find out how to make it, and they can find out the impact on the environment just by these quantum trained AI models. Now, to get there, though, we'll not do that with what we have now, physical qubits, NISQ machines. We need to go to logical qubits, and then to level 3, we call it scaled quantum supercomputers. When we build them, then the question is, how do we build them? And that's the second point where the industry comes in. These quantum computers will be accelerators like GPUs, FPGAs, or quantum. They will be machines in data centers accelerating the way we compute. And thus, when we build it, we have to build it in the same way we build classical supercomputers. We can take the same full stack we have now from the workloads, the developer tools, the AI agents, the cloud services, and all, and into the system. At the bottom, in addition to all of the classical compute infrastructure, the supercomputers, the AI machines, we plug in a quantum computer. Building those will need the resources of your big companies, and thus then what the business can bring is it can bring the skill and the scale to build those machines. And that will then allow us, for example, to change how the chemical industry works, how biochemistry, pharma works. I want to have a co-pilot or a ChatGPT where I can just type in, create a new material to capture carbon from the air. And it tells me something that works. That's the future I'm dreaming of. Thank you.
Thank you very much. Very comprehensible and exciting to understand. So all those different approaches that we need to take into account while understanding this evolution as well. So this revolution, this quantum revolution. So thanks a lot for that. So indeed, this is a well advanced already world, so that Microsoft has reached out. So now we would like to hear, so our second keynote speaker, so with Professor Obasi Shira. So we have the pleasure to have you here with us, and you are a leading experimental quantum physicist at the Raman Research Institute in India, a Canada Excellence Research shareholder and founder of the QSIN technology. So your pioneer work in quantum optics, interference and communication, has pioneer, at the front of the Indian, rapidly growing quantum research and innovation ecosystem. So Professor Shiras plays a pivotal role in Indian National Quantum Mission and leads the consortium of institutional works towards entanglement distribution based on quantum networks. So after this second presentation as well, we will collect all the different questions in the Q&A, and be aware that all the questions that you could have to Matthias, we will answer them later on as well. So, yeah. Then, Professor Shah, if you could share your...
Thank you very much. Can you hear me?
Yes, we can. Thank you.
Let me share once more. Great. So thank you very much, Christine, for the kind introduction. And of course, thanks to IUPAP and UNESCO for this invitation. It's Diwali Day here today. It's the biggest festival in India. So what better way to celebrate than talk to fellow quantum physicists and industrialists. So this is what we're doing this evening. So what I'm going to talk to you about, of course, Matthias gave a very nice presentation on the possibilities of quantum computing and, what we may want to do with it and how to build it towards its, in its journey. So what I'll talk about is quantum at the speed of light, from prototype to product. I had a quick chat with Christine through email, asked her whether she wants me to say anything special. She said, no, say whatever you want to say. So then I have chosen what I want to do is, give you a little introduction to some of the touch points that we are going to elaborate on during the panel discussion that we're going to have for the next 1 hour. So I, of course, work with photons, and we are the first lab in India to work with photons and in all areas of photonic quantum information, including computing, communication, sensing, fundamentals. And the National Quantum Mission was already mentioned. We are all very excited by it, and of course, have been involved in it since the beginning, and currently leading a technology group of consortia of institutions on entanglement distribution-based networks. So very exciting times ahead for us in India and globally. So the first point that I wanted to, talk about a little bit is actually the topic of today's webinar, which is quantum for SDGs, right? Quantum for SDGs, quantum for society. How do we build quantum technologies for society? So this is something which inadvertently I have been actually involved in many panel discussions on this topic over the last few months for reasons that, I think it is just a very important topic. One of the things that I think has come out through all these discussions is that there is a particular need for us to mine the context gap, and this was already, in the first intro, we heard a little bit about the whole webinar. So we need to ensure that when we are designing these deployments, we don't leave the global south behind. And I, of course, like to pictures say more than words. So I think this is something that summarizes my own thoughts on this. So, on one hand, I have been actually, involved in the Open Quantum Institute in Geneva from the beginning, and now I'm in the advisory board. And all of us at OQI and CERN and various other institutions, we are very interested in ensuring that these technologies which we are building are actually built inclusively. Now, having said that, one of the things I realize is sometimes when we think about inclusivity, we are not always asking the stakeholders what they need. So now, here we have, an artist representation of the global south. And if we are building technologies, are we actually going to be able to deploy them as is? Are we going to, even have the ability to, have the cost to maintain those things? Do we have maintenance costs? Do we have connectivity? So we need to ensure that the technologies that we build pertain the problems in the global south. And so for that, we need to ensure that we involve more people from this designated areas in our dialogue so that ultimately we don't end up with some kind of a north-south divide, which is what we want to avoid, obviously, through all these concerted discussions and developments that are going on. So this was one of the points I think we're going to discuss quite a lot in our panel. The next thing, of course, which is the main thing, I just wanted to give you an example of how, I personally, being a very, very strongly academic individual, have always been in academia, have taken a leap and started my own startup, co-founded a startup on quantum technology. So I wanted to give you a little story on how that happened in India at our lab at Raman Research Institute. So with that, I go back to the Nobel Prize in Physics. It's a very important, Nobel, this is the Nobel month, right? And so this was in 2022. It was also given to quantum information, and these three gentlemen and their groups who won it for establishing the violation of Bell inequalities and pioneering quantum information science. So what they did specifically, so you can find more details in these write-ups, is what are called the loophole-free Bell test. So this was the Zeilinger experiment and so on. So what is a loophole? Now, it would seem like we are in some kind of a legal discussion, but we are not. But the loophole-free is nonetheless very important, even in quantum. So what is a loophole? A loophole is a fault, right? If you're in a court of law, you find a fault in some argument, and till one person has a faultless argument, the case goes on, and then you win the case with a faultless argument. Likewise, in Bell tests, if you have a loophole-free Bell test, then no eavesdropper is going to be able to come in and hack into whatever it is that you're using these technologies for, whether it is secure quantum communication, unhackable source of truly random numbers, and so on. And so this is why a loophole-free test is very important. And of course, but one thing we have to remember, even if you're not directly working in this domain, is that in order for us to do loophole-free Bell tests, the two parties need to be separated by a certain distance, currently at a 200-meter, scale, because otherwise the locality loophole is not closed. So if you have to be that separated, then think about how you would make a device which is 200 meters long. So then it doesn't lend itself naturally towards the product at the moment. This is where I would say our humble discovery comes in, which was, of course, Sir Anthony Leggett and Anupam Garg. They came up with the Leggett-Garg inequalities. I won't give you a science lecture here. It's a very short talk. But the Leggett-Garg inequalities are actually the time equivalent of the bell. Okay, so in Bell, we had these particles separated in space. Here we have a single particle moving forward in time. And so, of course, you don't have this concept of distance anymore. And so our group in India was the first lab to have demonstrated a loophole-free violation of the Leggett-Garg inequalities. And this was something that over decades people had been trying to close loopholes. So we are very, very proud that we were able to do this. And so this is what I would call, something which happened a few years ago and in the genre of discovery, right? But then we followed it up. This is beautiful. For the physicists, you will see the match between experiment and theory and you'll feel happy about it. But then, of course, went the discovery to device. Okay. And so what we went on to do in early 24 is a paper we published where we showed how we can use this loophole-free architecture that we have now using optics to generate semi-device independent random numbers. Now comes this point that, if you want to do the same thing using the Bell, these are all the seminal experiments that have happened, right, in the Bell literature. You can see the distance here. So the distance is usually in the genre, in the ballpark of 200 meters. Whereas in our case, it's a device which is sitting on a small portion of an optical table, which is doing something similar by using time instead of space. So this is what I would say was the first victory for me in terms of, doing something which is useful beyond my lab and beyond my scientific community, which is what we have been worrying about since childhood and in the sense child scientisthood. And so then more recently, what we have done is we have taken this device and put it on a quantum computer. This is an IBM device which we had access to, where we were able to show the same violation and generate the semi-device independent randomness now on a commercial device. So this means that, it is validated on something which we didn't even build. So now we are ready. Yes, okay. So we have done the foundational experiment. We have done the demonstration, the proof of concept. Now we want to make a product out of it. And so that is the genesis of QSIN Technologies, okay, which is actually a story of foundational validation to practical certification and deployment. And this is Team QSIN. This is I'm very, very proud of my, leadership team here. And in fact, two of them are with us on this call. Thanks to you for coming in on Diwali. And so they are all, either, future leaders or current leaders in quantum or business leaders, right? And so it's good because then, my business sense need not govern QSIN. My business sense is not known to be great. So then, so this is where it's good because we have this synergy. So far, in all that I have said, and this is our, the array of products that we are currently building, and this Q range that you see on the left is based on this lab to market idea that I just spelled out for you in the randomness domain. Okay. So far, all must be well. I mean, whatever I've said so far, your conclusion will be, oh, this is very nice. It's a very nice thing. In India, we have done this bottom up, and now we are ready to sell to the world. Of course, that is not how things work. And this is something we will be discussing quite a bit in our panel. What are the problems that we may be facing? Not just QSIN. QSIN is an example, but what is it that prevent? I mean, how can we bridge academia and industry better? Because currently, clearly, it's not like it's all smooth. And so one of the, again, I like my cartoons. So this is an example. So this is, I mean, this is representative of who, I have to have gender balance in my slides. So this is the QRNG that I just talked about. We have the lab, we have the field trials, we have the beautiful product, we have real lineage. But then we actually are in a hype cycle for quantum right now. And so what is also true is that because of that, there are many who have come up who are excellent in their business sense, who don't understand quantum, but then they have access to the photos and the buzzwords from the internet, beautiful websites for their companies, but not much products to sell. But then we are actually trying to compete against them. So we need to outlive the hype cycle. The real startups, who have come out from something real and quantum need to outlive the hype cycle. The other thing which, we particularly face, I'm sure it is a global phenomenon, that, the knowledge about what is quantum, although all of us are trying very hard to appear in all these discussions, many discussions, to try and bring policy and science together, but the policymakers have less time than us, yes, and so they don't always spend time in listening to what we say. So then we are saying, okay, this is certified through laws of quantum mechanics, we are ready. But then, of course, questions come. Does it run on classical benchmarks? And, the legacy assumptions are hitting us, right? And so, of course, we are telling little, slowly from the side, that's not how quantum gets this advantage. It is because it's certified by something purely quantum. That is how we are there. I mean, if I have a quantum product and if Christine has a quantum product, and it's not like if we know each other's products, we are going to hack into each other's systems simply because quantum mechanics is going to prevent us from doing that. Okay, and so this is something not so clear. So there is all this confusion about what is dual use, what is not. And so this is also preventing us a little bit from really going out there and being able to declare our products in a certain way and gain momentum for our products, because there is a little bit of lack of reception, let's say, sometimes from the policymakers. So we need to keep on with our efforts to make this available, to make this divide happen, become lower and lower. And so I think, that is what I think sets the ball rolling for our panel, because, here we would like to come up, I mean, I'm sure we won't come up with solutions, but at least some discussion points on how we can ensure that we build quantum technologies which are for the world, not just for one region or the other, thinking about it in an inclusive way. How we can ensure that academia, industry, and policymakers see each other under the same platform, so that whatever little we do is for the good of society. So I hope that serves as an intro with Matthias's intro to our panel. And with that, happy Diwali. Let there be light, let there be quantum.
Thank you so much. Extremely clear, and thanks a lot also to give this recipe as well, or to think out of the box as well. So that's how we can maybe address all those different questions. So we have some that are peeling up, so that's good. So in our Q&A. So now, so this is the time, so when we will have the possibility to hear more of our panelists. So we will introduce 4 more panelists. So first, so Dr. Sarah Sheldon, who is the principal research scientist and the head of applied quantum science at IBM Computing. So her expertise includes quantum characterization and techniques extending the capability as well of current quantum system. So she now focuses on developing novel algorithm and application for quantum computing, contributing as well to this IBM global leadership in building practical quantum computing system. So that's in addition to Microsoft, a nice view as well. So we have as well with us so the chance to have Dr. Mark Jackson, who serves as the senior quantum evangelist at Quantinuum, so where he promotes so the application of quantum computing across industries and academia. So with a background on theoretical physics, so he is dedicated to fostering global engagement, understanding of emerging quantum technology. So the Quantinuum, so it's a US headquartered location, so for the company, but they have also office in the UK, in Japan, in Germany, and soon in Singapore and Qatar. So that's also an important way how to get more global access. So the next panelist that we have with us also come from bridging, I would say, Africa and the New World, so in Canada. So Estelle Inac, so Dr. Estelle Inac is the co-founder and the CEO of the Yin Yang KQ, so sorry for the maybe wrong pronunciation, so which is an AI-driven quantum software company. So she was born in Cameroon and she earned her PhD in Trieste before becoming so researcher at the Perimeter Institute, so in Canada. So she combined artificial intelligence and quantum computing to develop innovative computational tools to study quantum, many different, many bodies system, and to solve the quantum optimization problems. And Dr. Inac is also an ICTP alumna, so International Center for Theoretical Physics in Trieste. And our last speaker, our last guest of honor, so is so Dr. Isera Ismail, who is a senior lecturer at the research and a researcher at the Stellenbosch University in South Africa, so specializing on quantum optics and quantum communication. So the photonics labs, so where she advanced also the different research in quantum optics and secure quantum communication. So her team established the very first quantum satellite link in the southern hemisphere and the longest intercontinental quantum links. So that is really a driving force, so that she's representing. So in Africa quantum research community, and she serves as the Optica Vice President on the International Commission for Optics, and she's a member as well of the South African Jones Academy of Science. So they are the panelists that we have the honor to have with us today. So then looking at this communication that we'll try and start to initiate with all of you. So I will start first with Sarah Sheldon. So to try to have her insight as well. So in terms of how can we explain more and how we can balance this open science collaboration with the protection and intellectual property in this quantum tech. So what do you think, Sarah?
Yeah, thank you, Christine, for the question, and thank you for having me here for this discussion today. I think when it comes to collaboration and IP, the key word in that question was balance, right? So I think you know, absolutely, as researchers, you know, many, probably all of us are coming from very academic backgrounds where we really value collaboration. And I think we understand that collaboration and building ecosystems around quantum computing is going to be absolutely essential for driving this technology forward. We're kind of at a place in quantum where technology is maturing and companies are thinking of, you know, how will business models work, where are the areas where quantum is going to offer the most value, and ultimately building, you know, plan strategies that will have to get return on investment at some point, right? This is a huge project to build quantum computers and requires lots of effort, you know, and effort that's been going back years and years in industry as well as in academia. So ultimately, for quantum to be successful as a field, we do need the quantum business to be successful, and we need quantum to give value for people who would use quantum computers, right? So the IP concerns are important for industry and for you know, for building quantum businesses, but at the same time, you know, quantum is a technology that is still maturing, and there are a lot of open questions, and there's a lot of opportunity for new ideas in the field. So we can't have IP be restrictive. IP concerns cause restrictions in open collaboration. I think what we see is really kind of a delineation of where things can be very open versus where companies tend to have more proprietary focus. So speaking about IBM, I work on our algorithms and applications mission. We are very collaborative in this space. You know, we work with other quantum experts. We work with domain experts who, you know, have expertise in chemistry or material science, or, you know, have interesting optimization problems. And this work can be very open. We are very interested in working, you know, together with academics, national labs, other industry partners for pushing new algorithms and for identifying good problems for quantum. You know, we also have a full stack product from IBM, and different layers of the stack are going to have different IP considerations. So, you know, software, we work on our open source software development kit, KISS-Kit. There's lots of contributions that are open here. I think what is really proprietary and where you know, IP is more of a concern is really at the device level, right? So we're less interested in an open device business. That's really, you know, that's really where there's a lot of differentiation between competitors, and where we're leveraging a lot of IBM expertise. but that doesn't mean that there's not parts of, a quantum computer that's not open for collaboration. There's all these other components besides the quantum processor itself, right? So all these other elements, and even, maybe longer term research on things like transduction and parts of the hardware stack that will be important to our roadmap down the line. We're certainly open to collaborations. I think the main thing I would say in thinking about IP is really being clear and delineating what is open and what is not. And when we collaborate, having that communication and establishing those boundaries up front is very important. I think people have the experience of talking to people and then all of a sudden something's off limits. It's good to be open up front. And the main concern is that we don't have IP constraints that prevent us from using things that we're developing going forward. So it really is about balance, but I think this is a field that's going to continue to really be driven by the community and by collaborative efforts. And we need to not be overly restrictive, but make sure that we're working towards building quantum businesses that can be successful.
So indeed, this is a perfect answer. So indeed, the balance and to find the limit, but not too much limit, and then to set up as well the rules and then the organization of the society that would help integrating this in our society. So thanks a lot. So now indeed, we have a question for you, Mark Jackson. So how do you think that quantum technology can help addressing the sustainability challenge? And in which sector, for instance, like we have the energy, the healthcare, material, or climate, what do you think should we focus first on? What would be easier potentially?
Yeah, so the good news is that quantum computing is a tool which should have a lot of positive implications for things like sustainability. Things that have already started to be researched are, so first of all, like in the energy sector, things like superconductivity, so like higher temperature superconductivity. So we know it exists already, but maybe we could study how it could be achieved at higher temperatures. Nuclear fusion, we've seen a lot of headlines about this starting to make progress, and maybe we could model this better. Things like petroleum refinement and greener energy, things like fuel cells and batteries, obviously, especially with electric vehicles and the aerospace industry. At Quantinuum, these are things that we've researched more or less already in each of these. In terms of mitigating climate change, there's actually the possibility of extracting CO2 from the environment using metal organic frameworks. And this is actually what the Chemistry Nobel Prize was just given on, so metal organic frameworks, MOFs, they were kind of described as like this Harry Potter-like bottomless vacuum of being able to absorb things. And so we can extract CO2. And this is something that we've been working with Total on already, as well as with fertilizer. So the most valuable chemistry problem in the world is actually fertilizer production, but we're very bad at it. We spend about 2% of the world's energy supply just making fertilizer. And we hope that by using quantum computing, we could do molecular simulations and figure out how bacteria do it. So we could kind of mimic this. And then finally, in healthcare that you mentioned, drug development is one of the big applications of quantum computing, being able to model different drugs in the early stages before we do clinical trials. And that this was mentioned in some of the presentations a few minutes ago. We're already working with the Sanger Institute to do genomics research and really align AI and healthcare and quantum. If you were to ask me which I think will be the first, I really couldn't say, but I think it will be in chemistry. And the reason for this is because chemistry tends to have an exponential advantage in quantum computing. Other quantum algorithms sometimes only have a quadratic, but chemistry seems to be the most promising avenue. So I'm very excited about what's to come.
Very good. And chemistry always go with physics in one sense. So this is also the good aspect. So the need as well to understand everything, maybe so quantum liquid as well, or all those different aspects of also the material. And it's always pluridisciplinary in one sense. So indeed. So thanks a lot for this answer. So now I would like to address as well a question to Estelle Linac, so who is also joining us with so your different backgrounds. So what do you think? What a unique role do startups play so in advancing quantum technology if we compare the large corporation and the research lab? Any limit there that you see?
Thank you very much for the question. So I think the unique role that startups have compared to research lab and large corporations. So research lab typically advance fundamental research, and currently we see large corporation dominating more or less in terms of large scale research collaboration and hardware as well, or high profile POC, as we recently saw between IBM and HSBC. So I feel like startups sit more or less in the middle ground. So they are very much agile and they are risk-taking, which means that they can move fast very quickly, iterate on ideas, which large corporations are usually very slow movers because there's a lot of bureaucracy they need to go through to be able to move between one idea and the other, whereas startup can prototype, pivot, and test things very quickly. So this is one advantage. The other advantage also is that they can quickly go from research to product. So they can convert whatever fundamental research they have into a product that is actually usable for people to start basically benchmarking, be it in chemistry, be it in finance, in optimization. So they can basically shorten that path from research to industry, right? And so on the third part where I think that startups have an advantage or a unique role compared to labs and large corporations is market signaling, right? So through pilot projects, venture rounds, some of the POC that they have, basically they can signal to the market where quantum is in terms of industry adoption, which of course labs and sometimes corporations cannot do. So yeah, so this is the three areas where I think they play a unique role.
And maybe as well a bit less protocol if you are thinking as well on a startup or research lab, I guess.
Yeah, so that's the part of bureaucracy, I would say.
Exactly. Thank you very much. So maybe now next question will be addressed to Yasser Isma. So how can you look at what the international collaboration accelerate quantum-based solution, looking at the Sustainable Development Goal? So how can we do this acceleration? What do you think?
Thank you, Christine. And we just heard from Mark Jackson now about all the ongoing research and the potential of quantum technology to address the Sustainable Development Goals like zero hunger, good health and well-being, as well as climate action. And we all know that countries have their own quantum initiatives to develop and deploy quantum technology and to also address some of these Sustainable Development Goals. However, the development of quantum technology requires a lot of investment and it's substantially investment heavy. This can be a major challenge, especially for countries or developing countries, and especially for countries that don't have a strong quantum focus, that don't have even a quantum initiative. And the only way we are not going to create a quantum divide where we leave these countries behind as we address all these Sustainable Development Goals as well, which is applicable to all countries and needs to be addressed by every country, is that we need to create this international cooperation and collaboration to drive this global quantum ecosystem, because we know locally and nationally countries are developing a quantum ecosystem. How that actually is portrayed, we all are going to wait and see how it unveils or unpacks itself. But we don't want to create a quantum divide where we leave developing countries out of this drive to develop a quantum ecosystem. And that is why we need to see how international collaboration will play a role. And I really feel it will play a role by pooling global resources and expertise, especially to overcome this immense cost and complexity with quantum research, to enable breakthroughs, to allow researchers and institutes in developing countries to also be involved in the deployment of quantum infrastructure in their countries. We really need to look at Also, the fact that, you know, all solutions are not going to be same for every country, right? If we look at sustainable development goals, specifically, if we're looking at agriculture and agriculture modeling, that may not play the same kind of parameters in one country as opposed to another country. And so if we're looking at how we're going to address these goals and create quantum-based solutions, we also need to provide infrastructure to those researchers in the country. And we're only going to be able to do this through international collaboration. The access to quantum computers is expensive. Some countries may not have the resources to pay for access to quantum computers, for example, to do the modeling. But if we have international collaboration, then countries or developing regions can access cloud-based quantum computers, even if they don't have the resources to pay for these cloud-based access on their own. So it's really going to come down to international collaboration to assist all countries to be part of this quantum ecosystem, not to create a divide. Also, you know, when it comes to education as well, we talk a lot about addressing sustainable development goals. One of the sustainable development goals is education. And not all countries have a quantum focus. Some countries may not even have lab facilities. And I know some of the African countries are still developing even their classical lab facilities, let alone the quantum lab facilities, right? And so if we're looking at the expansion of quantum technology, we also have to focus on quantum education. And we need a lot of international collaboration to expedite basically the transfer of expertise through international training initiatives to basically expand the global capacity of quantum researchers, so that we don't create an environment where we're leaving some countries behind. So we have a strong focus across all countries and ensure that we have a quantum innovation that's widely distributed. The other challenge, and I think someone picked on policy today, and that's also standardization of quantum technology. We're not going to be able to standardize quantum technology if each nation is going to try to achieve this on their own. It's going to be completely a global effort, an international effort to standardize technology so we can develop this quantum ecosystem. So hopefully through this interconnected actions, we can really not just focus on national efforts, but a global coordinated quantum ecosystem. Thank you, Christine.
Thank you. This is a perfect answer indeed. This global south, global north as well, collaboration and all those different networks as well being built and supported. This is exactly what the IUPAP and UNESCO also is trying to empower. And education, as you said, maybe some kind of co-tutel that could happen as well between the European part and the American for the global south as well. So there is a lot to develop. So that's excellent to have described all of that. So now I'd like to come back as well to another question as well, so to Matras Troyer. So this is also interesting to understand the different barriers. So what do you think? So what are the main barriers preventing the quantum solution from being applied to real-world sustainability goal?
Yeah, I think there are two barriers. One is we need the scale quantum computer, hundreds the fastest, the logical qubits, and that will still take some years. So we don't have the hardware yet. But I say that if we had the hardware now already, there's a bigger problem, and that is we need to actually think through what are the use cases, what are the problems we can tackle, and how. In the quantum field, the focus has been on building qubits, building hardware, and on quantum algorithms. But there hasn't been much focus until recently on the applications, on what are really the problems and how do I solve them with using AI and quantum algorithms. So we need more people actually who think on how will we apply quantum computers to real problems. And that's why with the X Prize we launched the Quantum X Prize to incentivize the quantum researchers to work with to talk to domain specialists, to learn about the SDGs and find new ways to apply quantum there. That's why with Nechester we launched the Open Quantum Institute to bring more education about quantum also to the global south, because we need to have the people who understand the problems and to understand how one could potentially solve them with computers, learn about quantum as well. So I'd say the biggest challenge is we need to educate more people in basic computational science, learning how to tackle problems with computers, and then how quantum computers can help there. That, I think, is the biggest barrier.
Very good. And this is also maybe another way of thinking. So that's also this different evolution as well. How can we adapt as well those way of, getting an answer, let's say. So thanks a lot. So with now Orbasi Singha, so that would be really nice to understand as well. So can you elaborate a bit more on what the mechanism could improve the technology transfer from the academic research to the commercial innovation?
Sure. Thanks a lot for this question. First of all, we need to understand, because of course I'm from the academic world, so not all academic research does lead to commercial innovation. So we need more translational nuclei within the institutes, who can guide us on the suitability of this translation, so that only those which seem to fit all the criteria other than academic excellence go to that next step. So that would be a good thing. I don't think we have enough of that in every institute, at least from in the Indian perspective. Then I think we also need more incentives for the researchers. So as researchers, we are happy with our refereed publications and disseminating our research to our peers and so on. But then if commercialization is a suitable next step, we should have incentives like royalty and equity sharing, promotion credit for patent standards, field pilots. It shouldn't be that suddenly the academic contribution is forgotten when it goes to that next level. That can happen inadvertently sometimes. So that is one thing. Then missions that countries are coming up with, they should have these mission aligned proof of concepts which have these specific markers, which need not only be paperwork generation, but then actual TRL levels which are achieved as we go along in these mission objectives. And this TRL is also a very important thing because most of us in our academic hat, we reach TRL 2 or 3, right, in what we do. And then of course we are supposed to be at a 5 or 6 before it goes to a product level. But there are very few bridge grants available which take us from this 2 or 3 to 5 or 6. So this sort of a bridge grant, I think is a great idea, because it helps not only the academics but also the startups which spin out of our labs to actually work more to take it to that higher level before making it into a hardy a product which is available to people. Then another thing which I can think of is a co-funded funded pilots between academia and industry. So whether it is defense, so the actual the user community like defense, banking sector, these are the ones I can think of because I come more from the communications perspective. So if we have co-funded pilots, then it is beneficial to both, and if something good comes out of it, then naturally it can go to a commercial innovation scale. Maybe have co-funded also people mobility between academia and industry, because people who are trained in the academic sector, I must say with due respect, we do try to ensure that they know what they're doing. And so then these are great assets for the industry, but sometimes if already they are doing some co-funded pilot, then they can get absorbed, and this is also good for the overall human resource, which is a very important problem globally for us. And then another thing I think that I can think of is that if we could have these outcome-based pilots, because sometimes some of us, if we are in our academic hat, we are a little bit apprehensive in getting into some kind of a project with the industry. We think, oh, we don't like to fail, right? Like academics are a little bit of have a little ego as well and all that, right? So we don't want to fail, but that's not the idea. So if it reaches a certain maturity, it goes to the next step. If it doesn't, then it's a great, output from academia, and then we go on to something else. So this sort of a flow chart, I can think of a decision box, yes, no, I think if we could have such a mechanism naturally coming into various schemes that we come up with, then I think we can have more technology transfer between academic research and commercial innovation, because I do believe, as other panelists and even the hosts have said, that the bedrock for something as deep tech as quantum has to be coming from academia, because there is a lot of deep tech in what we do. So naturally this leads itself to innovation, but some of these pathways need to be better formulated in my mind. Hope that answers to a certain extent.
Yeah, perfectly, because this is exactly those kind of magic solution that everyone is looking for, but you have like given a kind of sequence that has to be thought for trying to enable as well a successful mechanism. So thanks a lot. Thanks a lot. Now, so back to Sarah. So Sarah Sheldon. So what do you think? So what condition turns those breakthrough research into widely adopted global technology in the case of IBM or beyond?
Sure. Thank you. Yeah, I mean, I think, as researchers and scientists, we like to think, the data speaks for itself. And if we have a great result, people will use this technology. And I think certainly there are technologies where that happens. If you look at technology like CRISPR, which in the huge strides in the past few years that very quickly got adopted by a community for DNA sequencing and gene therapies and all of these things. That was a technology that had kind of a community ready to go, like ready to adopt it, and really hard problems that it immediately solved, right? I think, we're working in computation where our potential users come from a wide array of backgrounds, right? So, if we say, at IBM, we have on our roadmap, our first full-scale fault-tolerant system is scheduled for 2029. And if we tell people, hey, we have 200 logical qubits, you can run 100 million gates, what are you going to do with it? Most people don't have an answer for that, right? So I think it's really important that we're building up this ecosystem of researchers who are, coming together from quantum expertise, but also domain expertise, in chemistry, in material science, thinking about even beyond quantum simulation applications, optimization. Optimization problems are some of the hard problems that you see throughout many different industries, and being able to identify which ones actually have potential with quantum is work that needs to be done collaboratively. Quantum's always been, I think, a very interdisciplinary field where we've always had computer scientists, physicists, mathematicians, but we also need, chemists, high energy physicists, like all of those people who would use quantum computers to become, the computational scientists who would understand how quantum applies to things. And we need to also make things easier for that adoption, right? In terms of having systems be accessible, in terms of educating those user groups, and ultimately having, those interfaces like the applications libraries and things like that will, like we have scientific libraries for using HPC today, and similarly for AI today. Like all of those elements of making things easier to adopt are going to be really important. So it's not just that we have our results, and when we have, we put out the systems and we have maybe some milestone experiments that we can do ourselves. Those are great for generating interest, but ultimately we also need to really build up communities that will use quantum computers. And maybe just to talk to one example of that I'm really happy about is the quantum working groups, which IBM helped found, but are really consortiums of many different industry participants, academics, etc. we've helped found 5 different working groups that range from high energy physics to healthcare and life science focus. And it's really a coming together of people thinking about how would they use quantum, starting to learn, how do you map a problem onto quantum? But ultimately, is going to evolve over time. How do these communities work together and identify those good problems for quantum and build up skills and all of those things?
Yeah, this is perfect. So this is very interesting indeed, the structure, how also communication or maybe with some standard as well, like it should be the SEM or STM of the quantum to be developing as well. So, and then maybe across the different continent as well. So depending on the need. So there is certainly some work to do there. Indeed, more standard. So Mark Johnson, so what do you think? So how can better alignment be achieved among university, industry partners, and policymakers in the field of quantum? So from those 3 aspects, how can we better?
So my first suggestion would be policymakers need to understand what quantum is. I can't tell you how many times I've spoken with policymakers, and I know their intentions are good, but they don't really understand. First, they understand that quantum is a different type of computing. A lot of times they think it simply means faster. And the second thing that they should understand is that it's here. It's reality. This is not science fiction that might be relevant in 20 years. It already exists, and it's quickly becoming commercialized and practical. So first, I would just suggest that policymakers really understand what it is. The next thing I would suggest is having some standardized benchmarks. I've noticed the past few years there's been a lot of kind of hype and positioning and claims which are not really founded on reality about quantum. And I understand why that is, because until very recently, it has been largely research and theoretical and things. And so people kind of had to just talk about what they intended to do. And that's fine, but I've noticed, especially the past year or two, that it can be misleading. And it's like, I'm a physicist and I work in the field, and even I sometimes have trouble kind of figuring out what they mean, or the caveats, or the way that they're splitting hairs about something. I think it should be clearer to someone, especially a non-technical person, what is actually happening and what can be accomplished. And I think that will change very soon as it becomes more practical. I think, if quantum computer A can do something that quantum computer B can't, I think that will quickly become obvious. So I think it's going to kind of self-correct. And then for people in the industry, I would recommend they just work on projects, that they work with a quantum computing company to do some use cases and kind of proof of concept projects and things. And it doesn't have to cost millions of dollars. At a pretty reasonable budget, they could at least understand how quantum will affect their industry and kind of build up their quantum expertise and quantum muscle. So yeah, those are kind of my quick suggestions of how to integrate those 3 areas more.
Yeah, very good. So indeed, exchanging expertise, and maybe to have also a library or language that would be like helpful for every of those different disciplines. Indeed. So, and the library aspect, I think, is a good one if we can like have a common language. Indeed. So with Estelle, Inac, so what do you think? So what are the biggest challenge quantum startup face in scaling up, so attracting investment?
Yes, so there are a couple of biggest challenges. For early stage startups, for example, I would say the biggest challenge is the so-called chicken and egg problem. Because to be able to attract investment, you need to demonstrate that your technology works, right? And to demonstrate that your technology works, you need people working on that. So you need talent, right? And to have talent, you need to pay them. So you need funding. And to need funding, you need to show that you have traction. To have traction, you need to demonstrate your technology works. So you have this cycle that you need to break, especially when you're early stage. And so that's one of the biggest challenge, and it was already mentioned. So the other challenge is to demonstrate that not only it works, but it's useful. Because unfortunately for startup, you don't have the luxury of just going about with proof of concept. At some point, you need to show that whatever you're building as a product is working much better than whatever is out there. For example, if I think about optimization problems, people have been solving and people are solving optimization problems. So is your quantum solution much better? Is it faster? Is it cheaper, right? So if you don't show that, you at some point you will not be able to keep, attracting investment, right? So the other problem is there's a long time to market in the quantum industry, especially on the hardware side. So your investors need to understand that, the return cycles are longer, they need to be patient. And this is probably one of the reasons why we see much more government fundings and government initiatives, because they can, they can wait for seeing a quantum value at a time. So for quantum software or algorithm, there's also a longer time scales than typical like just software companies, because not only you have an algorithm, you need to be able to have, you need domain knowledge and show that actually it's much better than what they are using out there. So your investors need to understand that. There's an issue with communication, it was already mentioned, not only with policymakers, but with investors and end users, right? A lot of people, quantum physics is complicated. A lot of them don't understand it. Sometimes we are not doing startups a good effort to educate them to understand what is possible, what is not possible. And the problem with that is that there's a backlash. There's a lot of hype, and then investors, they have been investing and now they are not seeing the return, right? And so that can slow down the next round of investment because of all the hype that we are seeing. And then, of course, there are geopolitical factors. Quantum now is, you have export control, is dual use. So navigating all of these cross-border collaborations to be able to attract funding, that is also kind of a challenge one has to navigate right now. Yeah, so these are some of the challenges I think startups have.
Indeed, so a lot of challenges, and maybe as well the cultural challenge. So I guess that also it's generation. Now it becomes like we have no choice but to integrate, but still, I guess that it will be time to changing as well, the mentality. So then we have a last question that we would like to raise to Yasera, so Ismail. So what example of successful cross-sector collaboration can we learn from?
Thank you, Christine. So, and we're going to provide you a comprehensive list. I'm going to touch on a few game changers in terms of deployment of quantum technology, as well as a few early adopters that has made breakthrough in quantum technology. And we have to start off, I think, with the United Kingdom's National Quantum Technology Program, which I think a lot of countries model the quantum initiative around the UK's model and the UK's program that's launched in 2014, which really was a good coordinated effort in partnership between government, academia, and as well as industry to basically accelerate innovation. And one of the deployments that came out of this quantum initiative was they implemented the first quantum secure network in Bristol. And this was enabling secure data transmission of critical services in partnership with British Telecommunication, Toshiba, and the University of Cambridge Quantum Communication Hub. They also deployed quantum gravity sensors for underground mapping with the University of Birmingham and Teledyne, ETB. Most important from the UK program was the thriving quantum startup ecosystem that they developed. If to date, there's about 75, I may be wrong, but 75 quantum computing startups alone that basically thrived out of this quantum ecosystem. So they really show a good model for the development of a quantum startup and the thriving quantum startup ecosystem. I would have to mention here SK Telecom. So SK Telecom is a company in Korea that deployed QKD over 5G infrastructure, and they did so in collaboration with ID20, and this was a 330-kilometer link between Seoul and Daejeon. And I mentioned this also because ID20 was one of the few early adopters in terms of companies where they started deploying quantum technology, making quantum technology commercially available. Back in 2010, we in South Africa also partnered with ID20 to implement the first fiber-based QKD link of 24 kilometers during the FIFA World Cup, 2010 FIFA World Cup. And it was the first time South Africa had a small QKD link of 24 kilometers, but it just showed that they were the early adopters into the deployment of quantum technology. And then if I really have to focus on game changers in terms of quantum communication, then we have to look at the MISSIUS project as well, because when the launch of MISSIUS and the first quantum satellite, this showed that, you know, it's the first time feasibly that you could send single photons from a satellite down to an optical ground station to deploy a QKD link. This also was the first time a country, China, showed that it's possible to do entanglement-based QKD using a satellite and optical ground station. China also has the quantum backbone fiber network of 2,000 kilometers between Beijing and Shanghai. And we know that this network is also being used by commercial commercial entities such as government, the financial sector, the energy sector. And so they've really created an integrated quantum network. And the last, I think, example I would like to mention is the most recent results, I guess, is the 12,900 kilometer quantum secure link between Beijing and Stellenbosch University that was possible through the Jinan-1 satellite launched by China as well into the lower Earth orbital. And the reason why this was such a successful example to mention is because for the first time we were able to implement real-time QKD. Previously, even with MISSIUS satellite, the QKD link was deployed, but the QKD key was only being able to be created 2 to 3 days later due to the fact that we're using microwave bandwidth in order to do post-processing. But with Jinan-1, within 8 minutes of the experiment, a key was produced that could be used to encrypt information, in our case, images. And it was the first time that marks the quantum link between the northern and the southern hemisphere. And so these are not in all a full list. I know IYQ has this 25 most recent quantum achievements for 2025, which I hope everyone can look at. But this is just a few examples of cross-collaboration that really has shown scientific advancements. And I think that's the most important part is that, you know, through cross-collaboration and international collaboration, we're really going to push boundaries and basically contribute to the sustainable development goals and achieve scientific breakthroughs.
Yeah, very good analyzing of how all those things can progress as well. So very good. So we have also so few questions from the audience. So it was nice to have so all our speakers answering them. So by directly writing them in the question and answer. So I think maybe I will save this and we could share it later on. So to share with maybe our audience. Maybe we could then to finish, so to see if anyone would like to have a live question within the panelists to each other. Was it any kind of new ideas that could transcend so your problem or challenge? Maybe not. But in any case, so what I wrote as well is the fact that Professor Yasera Isma will give also a more, I mean, a bigger and more elaborated presentation. So on the 30th of October, on the platform that we have with the American Physical Society on the Forum of International Physics. And that will be very nice to hear more about all those links. And I think it's essential as well in Africa as well to have this kind of niche as well. And all this knowledge, so to be able to share. And again, one way to understand for a solution, so from potential for this global north, global south, so connection. So thank you very much. Maybe I see that they are in the question and answer some comment. I think it was more a comment, so in German, so aus Deutsch, so it might be for Matthias Troller, so I think, but do you want to translate it for us, or do you think that this is someone maybe you know?
Okay, so but I think that question was then also asked in English and answered by Ubasi already. Yeah.
That's what. Oh, it's perfect. So the person then have the answer. So thank you very much. And then there is a last question indeed. So given the challenge that quantum thought faced, so the highlighting, so that so Dr. Estelle Isnak had done, so specifically needed investment. So do we have any advice on how to encourage and push for startup to engage with organization and policymaker to ensure sustainability and fairness, such as the collaboration? So with the OQI and the presentation and the presence of those panelists, of those panels and others. So that's the last question. So I don't know, maybe Estelle, if you would like to answer that one.
Yes, maybe I will quickly answer. I think I'm feel a little bit mitigated on that because it really depends which part of the world you are, right? There are some parts of the world where you have access to incubators, accelerators, that are great places to have resources and connection, mentorship, access to some quantum. When I think about, for example, Creative Destruction Lab here in Toronto, you can have access to some quantum hardware for free for a certain period of time. So these places are great places to be. Now in the global south, might be a little bit complicated, in my opinion. So maybe if you have like these global initiatives where quantum computing companies in the global south can also have access to some of those, quantum hardware companies via the cloud, that could help. I don't have an answer for that, unfortunately, for the global south. Maybe somebody else on the panel has. I don't know.
So would someone else also think in terms of answering to that question? Not simple. Huh? Otherwise, we have another question, which is general, that any maybe of you could answer from Duquesne course, asking, so if there are any scholarship opportunity for masters, so for the people who are interested in quantum. So maybe you can describe some of those programs that you know about. So who do we start by? So maybe with Obasi, do you know about in India?
Yes, yes. I think in India we have these very specific MTech in quantum technology programs, as well as MSc, and now we have also started this UGC, the University Grants Commission. They have started an sort of India-wide introduction of quantum technology at bachelor's level as well. So there is a lot of educational initiatives happening under National Quantum Mission. And in India specifically, there are scholarships being given by the technology hubs. So we have the 4 technology hubs for the 4 quantum computing, communication, sensing, and materials, and so the technology groups together, they form the hub, and so there are open calls for scholarships for master's program as well as PhD, and of course it is competitive, but at the same time they're there. I mean, there are many such incentives, and more are coming up. And I think Matthias is actually typing an answer to the question, so maybe you want to speak instead.
Yeah, I mentioned that many the universities that have a quantum master program can also have fellowships, so acquire there.
Yeah. Okay, very good. So thank you. Thanks a lot. So I'd just like to ask just a very general question also, maybe also to Matthias. So speaking about indeed all this quantum computing, this is really an important thing, but now there is also this quantum magnetism, there is a lot of development, and with the case of neutrons, so neutrons that are perfect probe as well in this quantum world, so with this wave-like nature that make them like perfect to study the dynamics and the foundation as well of our scattering technology. So what do you think, and where do you think that in terms of knowledge and technology transfer, we should bring more capacity as well? Because I know that you had already experienced that. So if we look at the capacity of neutron with quantum magnetism or else, those quasi-particle excitation, how can we make them real?
Yes. So one reason why I moved to a company was that I said I need quantum computers to understand neutron scattering data for frustrate the quantum magnets. So it's the combination of the measurements with the simulation that allows for progress. So in the case of materials, they are super complex. There are thousands of atoms in there. So doing that brute force on quantum computers will be hard. That's when you that space, one looks at the simplified models, so-called effective models like Hubbard model, the Heisenberg model. But we have to compare whether the model results agree with the material, and that's where probes like neutrons are a great check for the simulations. So this will grow in importance as we build more quantum computers.
Exactly, and when we have even brighter source of neutron, like what we're doing in Sweden, so that's really like very well hoped. So then now we can conclude. So all these events. So thank you everyone to have attended. So and we'll give the final note to Professor Lina Pons to conclude.
Okay, thank you, Christine, and thank you everybody for your contributions. This has been very, very intense. So I wanted to summarize a little bit the main ideas. Matthias stressed that quantum computers are good for small data problems and that the future is hybrid, that we will have combinations of AI and other techniques and potential applications he described where for material science it could be applied for discovery of new drugs, but also materials that could be used for environmental applications. Then Urbasi described the way from basic research to a deployment of technology. And she stressed that we don't have to leave the global south behind and posed some of the problems that we face. In particular, she mentioned the hype that was mentioned several times that could jeopardize the advancement in this area. And she gave a very interesting idea of how maybe through funding it could be incentivized the way that people go from the academics to the technology world and can go back and forth, and the country and the world can benefit from that. Sarah addressed the problem of whether open science collaboration could be carried out in spite of the protection that companies need. And she stressed the need to balance these two aspects, that there are some aspects that maybe need some protection for the companies to invest, but also open collaboration, especially as researchers, is fundamental. And something she stressed was the need to build a community of users of quantum computing. And so that it's very important to understand what you can do with quantum computers, what kind of problems you can address. Mark also stressed the many applications of quantum computing. Also in material science, he mentioned high temperature superconductivity, nuclear fusion, green energy. And he also mentioned the need that policymakers need to understand what is quantum and what is the potential of this technology that is bringing so much attention. Stale talked about the uniqueness of startup companies, because so far we had heard about IBM and large companies. And she said that they are in the middle ground, that they are much more agile and they can move quickly, and that large corporations are slower and benchmarking is faster. But the biggest challenges are to find the correct funding, because, I mean, you don't have that background that large corporations have. Yasira, she addressed the issue of the collaboration across the global south. Very interesting examples of the collaboration between South Africa and China, and how this is key for the advancement, and also because not all countries will be able to pay to access quantum computing resources, for example, and through collaboration that could be done. She also stressed quantum education, something that other people stressed as well. And so I think there are many, many other ideas. I won't be able to summarize everything. And let me tell you that we are planning to have the last colloquium of this series focused on quantum science and technology for the International Year in December. We don't know the date yet because we are negotiating with the speakers. We hope to have 2 Nobel Prize winners in a dialogue to discuss the impact of quantum science and technology, and also of the year, the International Year. And also, Christine already mentioned that Yassir is going to participate on October 30th of an activity organized by the APS. And later on in December, Ana Maria Cheto from Mexico is also going to give a talk. So this has been a very active year, and I hope that the people who are watching this colloquium, those that are going to watch it, because we are going to put it on our YouTube channel, the IUPAP's YouTube channel. I hope they enjoy and they go back home with useful ideas. And I thank you again for your contributions.
Thank you, everyone. So it was really a lot of information that we have collected. Everything is online soon, and we'll keep in touch in any case. So thanks a lot for your attendance. And we have also the link as well in the chat. Thank you, everyone. Let's stay tuned.
Thank you.
Bye.
Bye-bye.
Thank you. Bye.
Thank you.